Good morning. Today I will give today the second lecture, and as our schedule, I will tell you something about the X-ray absorption spectroscopy. Today we will mention about these two. Quite often you will see in the slide that I write down such kind of abbreviation. XANES, that means the X-ray absorption near edge spectroscopy. And if you see this, it's EXAFS, that means the extended X-ray absorption fine structure. And if you see this term, XAFS, that means the X-ray absorption fine structure. X-ray absorption spectroscopy actually it's already a quite long technique in material science and biological science. You can see this mention about it has been known that X-ray edge spectra are related to the structure around the absorbing atom. And XAS means the X-ray absorption spectroscopy, was actively studied for more than four decades. With some clarity and some confusion. Yeah, that's I think many science at the beginning. It's quite often. There are some clarity and some confusion. And around 1970, Sayre, Stern, and Lytle, they put together the key element and that explain the XAFS as a short range order theory. This is related to try to compare in the diffraction. In last lecture, we're talking about X-ray diffraction. When you are talking X-ray crystallography, we use X-ray. We measure the elastic scattering, and that's a diffraction. And here we're talking. Once you want to have diffraction peak, that means in the material you need long-range ordering, so that you can get a diffraction peak. But here, in the X-ray absorption spectroscopy, it's a short-range ordering. That means in the structure, actually you don't need to repeat many. Thank you. You don't need like a structure, crystalline structure. You have many repeat unit cell. In this such technique, you can measure the sample and the liquid state. In liquid state, you don't have so many repeat unit cells. And so this is the XAFS is actually around 1970. They think it actually XAFS should be a short-range ordering theory. So please remember, this is different from the diffraction. X-ray diffraction is a long-range ordering technique to probe your structure. So that means you need many repeat unit cells, many repeat distance, many repeat pattern. Then you can get a sharp diffraction peak. I think for XRD pattern, diffraction pattern, you have such kind of diffraction peak. This is 2 theta, and this is your intensity. And this is for X-ray diffraction. Okay, and for this you need a long-range ordering. But for the XAFS technique, it's just a short-range ordering theory. And in 70, X-ray near edge structure was still puzzle. And over the next few decades, it became clear and the basic phenomena think in the extended X-ray absorption spectroscopy region. And here in the near edge, they should be the same. That means that you can use the same theory to explain the extended region and the near edge region of the spectrum. But some complication in the theory, such as large angle multiple scattering, tend to less pronounced in the XAFS than the near edge. And nowadays, once you want to explain the near edge structure, and you have to combine the theoretical calculation. And that include you use the multiple scattering, and also you need use some molecular orbital theory, and so that you can interpret the spectrum. It's not easy, but to the end we will give you an example how we interpret the near edge structure. And quite often you will see, if you see this XAFS, that means that's a combination of X-ray absorption near edge spectroscopy and the extended X-ray absorption fine structure. Before this, maybe we just review the short wavelength region of the electromagnetic spectrum. And here you can see this infrared region, visible, ultraviolet, and to here is X-ray region. We will focus on this region. And when talking about X-ray absorption spectroscopy, quite often we use the unit electron and electron volt. And you can find in this region, there's one, the right down we see it's soft X-ray, and the other one is hard X-ray. Okay, and you can distinguish this around the 1 kilo electron volt. If the energy is below 1 keV or near 1 keV, you can consider it's a soft X-ray. And if the energy is above 1 keV, and we call it hard X-rays. Okay, so once you go to synchrotron for experiment, maybe someone will tell you you're doing experiment is using high X-ray. Quite often, for example, you do the X-ray diffraction, and such as you do powder X-ray diffraction experiment, or you collect your sample data for protein crystal. Then we often use the wavelength about 1 angstrom. It's hard X-ray region. And with short X-ray wavelengths, you can see smaller feature. Like you can know the atomic the distance between atoms. And you can write a smaller pattern. And later we're talking about its elemental and the chemical sensitivity. Okay. In last lecture, we already mentioned about interaction between light and material. Now we go back this, and by this time this light becomes synchrotron radiation light. So it could be UV or X-ray. And when this synchrotron shows interaction with your material, and now you have to consider the material. We consider this material has a structure. It has certain structure. That means you have a absorbing atom. The atom will the synchrotron will excite your atom to the excited state, and it will have many physical process. For example, if an instant beam come in and shine on your sample, and the sample will absorb the photon. Then you get a major transmission beam, okay? And the sample absorbing the atom will make the material go into excited state. And once the material go into excited state, it will give out fluorescence and relax to the ground state. And so it emits the fluorescence, so you can measure the fluorescence here and obtain the fluorescence spectrum. And you have instant beam intensity absorbed by the material, you measure the transmitted beam, so you can measure the absorption spectrum. And the instant beam interaction with the material, and you can scatter the X-ray. So you can measure inelastic X-ray scattering, or you can measure elastic scattering. The elastic scattering, we talked in last lecture about X-ray diffraction. And so now we are talking about the structure. So you have to always think about what's happened when the X-ray interaction with the material. Before this, we will mention about notation, what quite often we used in X-ray spectroscopy. And let's consider these two pictures. And this one is there's just as imagine there's an electronic structure like this. And in 1s orbital, you have here in 1s state, you have 2 electrons. Here 2 electrons, 2 electrons. This 4 electrons. And when X-ray come in and then knock out 1 electron out, then you leave 1 hole. For example, now if the X-ray knock out 1 s electron to continuum state, then you leave 1 hole. So that means you have 1 s hole here, and the principal quantum number n equal to 1. And your angular momentum quantum number L is equal to 0, and you have 1 hole, so S is equal to 1/2. And then the J is equal to L plus S, so it's become 1/2. And in such case, we will write down this as 1s sub 1s, 1/2, like this. And if you excite electron, this electron is located at 1s orbital. We call it KH. Okay, the same as if the hole now it become at 2s, and then this 2s, so this n equal to 2, L equal to 0, and S equal to 1/2. So J is still 1/2, and you write down this 2s 1/2. And this one we write down is L1, L sub 1. Okay, and if this hole is created at 2p level, then here 2p orbital you could have such 2p 1/2 or 2p 3/2. Let's look at this one. If the hole is at 2p and n equal to 2, L equal to 1, and S equal to 1/2. And so now the J value could be 1/2 or 3/2, because the total J value L plus S is 3/2, and L minus J is 1/2. So the J value could have 1/2 or 3/2. And so this is 2p, so we write down this 2p sub 1/2 or 2p sub 3/2. And for 2p, then this one is L2, and then this one is L3. And this is for absorption. And for emission, that means you just have for example, this electron excite, and then you have another electron come back to fill in this 1s state, and this emission. Okay, now let's look at this picture. And this we are talking about energy levels, absorption age, and the characteristics 9 emissions for multi-electron atoms. And this try to correlate what you quite often you already know, K alpha, K beta. And we already mentioned in this, we already mentioned the meaning of K, L1, L2, L3. For K, that means you excite 1s electron, you knock out 1s electron, and you have a core hole at 1s. And L, it means n equal to 2, and 2s, and